this is a very interesting topic, but not belonging to the supervised regression, not belonging to the supervised classification, but it's very important. In the end, it's part of about representation. We're trying to learn a representation, how to represent our data points. So it's a very important topic related to both, and even related to unsupervised models. So what we're going to cover today, the approach for feature selection, what we're going to cover today, uses the label data. So that's why I put right in the middle between supervised regression and supervised classification. There's another group of approach doing feature selection or feature representation learning, which not relies on the label data at all, and it's part of unsupervised models. And so you can treat it as more unsupervised flavor. I'm going to talk about it actually after deep learning, maybe around that part, because the very important approach called PCA, it's a classic method to learn good representation, representing faces, image-based face categorization. So in summary, I separate the feature learning, the learning of features, not put them as one section, but just put them more like interleaved with regression, classification, and unsupervised models. There's a reason behind it. Just it's better to put them in the context of the other bigger tasks we're trying to cover. But honestly, if I'm teaching a deep learning course, and the representation learning will be a completely separate section to cover beyond everything we put it here. So, all right, so feature learning is not listed here, but it's a very important topic. It belongs to representation learning. But in general, we don't learn feature at all. So last time we covered regularized regression, just a little bit detour and not about feature learning. So on Piazza, there's a question about what loss do you plot or report? So the specific loss we are asking for are still the MSE loss, mean squared error. If we ask for training error, those are the mean squared error on the training point. If we ask for testing error, we are asking for mean squared error on the testing point, the mean, the average error. We are not asking you to report the scoring function plus the regularized norm. So there's a reason, right? So in the end, the purpose is to predict its prediction. And we ask for to plot the norm in a separate writing part to ask you to compare the norms. So, but we don't put the two things together. So in the learning, you are optimizing a SSE plus the regularization norm. Yeah, that's true. But when you trying to sanity check about what's the performance of the model, so we still use MSE on the testing data actually to evaluate. Because the purpose in the end is about generalization, right? And the norm is a mechanism to guarantee or to help us improve generalization. But our final goal is still generalization. We want our testing error, testing MC, to be low. And that's the thing we care. And the training error plots, the reason why I asked you to plot it, in the end, there's a reason behind, I'm going to talk about in the end of the lecture, is to investigate bias and variance of the model. Okay, so I hope this explains about the design of the homework 2. So we had a few updates about homework 2, and thank you very much helping me help us to stand for that type of frequent updates, because this is a new homework. So even though I added last year, but I think the requirements and it's much improved this year. And there's a lot of new things we added, like the plot, the epochs versus training and test era, and the training size varies versus the training size, as the training size varies, plot the training era and test era, and all those are based on the feedbacks of last year's students. And there's a lot of reason why we ask you, because those are good figures to help you understand, especially the theorems behind the bias and variance, and also the fitting curve. The fitting curve, how do you understand iterative algorithm versus those closed form algorithm? And especially for iterative algorithm, the training error or test and the test error, actual validation error versus the epoch, is a very good sanity tool for you to understand, is my iterative algorithm working good, working nicely on my data? So hopefully by the end of the homework, you understand why we're asking for those plots. So now maybe too early, because the majority of the student hasn't even started, but please start. And this is an extremely good homework. And it's about fundamental ideas, bias and variance and model selection. So even though we haven't talked about bias and variance, but I want to use a very concrete homework to give you a gentle introduction about empirical lookings of bias and variance. All right, question about here? About the homework 2? Nope. Okay, so let's go to today's topic is feature selection. So in fact, feature selection is a model selection. It's just I'm trying to select features. In the end, the derived model are different models if you think about it. So the task itself is we're trying to select P prime. So about this class, selecting P prime original features from the P features. Original features from the P total P features, and there a category approach, and actually a lot of tools provided. They roughly fall into 3 categories called filter-based, wrapper-based, or embedding-based. And the goal in the end, if you think about it, is we are trying to improve generalization, right? If the task is classification, we're trying to improve the classification on the future data. If it's regression, we try to improve the regression on the future data. Sorry. And so there are some levels of differences. Do you select one feature at a time, or you select a subset of feature together? Then how do you select a feature subset from a set of P features? If you are still remember your algorithm class, select subsets from a set is a classic combinatorial search task. All right, so we already introduced a few examples about why we want to select P prime features from P features. This is really just a setting. You have the data matrix, P n times P, and then you try to select only that square, that smaller yellow block, P prime, and make the data it's much smaller, hopefully use smaller memory, less memory, and computation more efficient. There are many cases need such kind of feature selection. The example we have, like movie review to revenue prediction, the gene expression-based patient classification. In this case, especially, we have very, very few number of labeled patient data, but we have extremely larger number of molecule feature representation, especially by the current genetic sequencing technologies. And this type of problem is acts more and more, but also the N is increasing. If you know, 23andMe, we have so many more subject level data, but still that feature is extremely, extremely large. And some other even vintage old classic type of problem, this text categorization. Actually, feature learning is extremely popular in text categorization tasks. For this problem, it's more like it's a news prediction task. there are 20 news groups, and then really just the web crowd text pages. We try to classify them into different type of news. If you ever use Google News, it's completely automatically classified into that category of classes. That's the very classic text-based news categorization output. All right, so why do we do feature selection? And we already emphasized this many times. We want to generalize well. We want to do prediction, classification, or regression better, because it's when you select less features and only the good features, the model is less sensitive to noise. And using the language of the learning theorem is the model has lower variance. And I will explain what do I mean lower variance later, but just keep that in mind is variance here normally means if my training data just has a little bit shift by adding some samples or by removing some samples, my model will be still quite similar. This type of model means low variance model. But if your training data just by adding a little bit noise, and your model completely change a lot, that means high variance models. And when you have a lot of features, actually the variance is quite high in the model, but I'm going to explain later. So this is still just intuitive introductions. Also, computational scalability and efficiency, we emphasized many times before. Of course, it's a smaller matrix, right? Of course, it's more efficient in terms of the memory cost or space cost. And if you remember that type of vector width computation, when you have a smaller p to p prime, of course, the computation cost, timing cost also got smaller. Question there? Okay. And then the last one is about interpretability. And this we emphasize many times because you have less features, it's easier to understand the features, understand the weights, just like the example we showed, right? The features, how the feature contributes to the money, to the revenue of the movie. If you have a huge number of features selected, it's really hard for the domain expert even to understand. And we want to have sparse models, fewer features, just important features selected. All right, so this all follows the Occam's razor rule. So if you ever know about it, we prefer parsimonious model, simpler models. We want as simple as possible, and the complexity should be just enough. And we don't want more complex model unless it's completely necessary. So this has a lot, don't even worry about it, just whoever know about this law, feel free to read it. Again, so where's the feature selection in our pipeline? So we have to talk about the normal pipeline. In this course, it's about training, right? About learning the model. And normally you have low feature sensing, processing, feature extraction, and then it's right after feature selection. But just to emphasize, this is an optional module. It's not just you have to have it. This is an optional module. If it helps, please include feature selection. All right, question? Okay. So now is how do you do the feature selection? There are three groups of approach. The first is called filtering approach. You want to rank the features independently from the predictor you want to use, and just based on, you either just select one feature at a time based on maybe correlations of the feature to the target labels. And that's just a very classic approach how to select features. Or you select a set of features based on their relationship to the target variables. That's called multivariate filtering approach. So there's also a second category of feature selection called a wrapper approach. So wrapper approach uses a predictor. It's a wrapper on top of a predictor. So you try to use the predictor to evaluate, is that set of feature important or not important? And there's a search flavor in both the wrapper whenever you try to select not just univariate features, or if you want to select subsets of features, and or like here or there, multivariate filtering approach, there's always an issue of search. What subset you search out of the P, a set of P features. So I'm going to explain more detail later. And the last category is the embedding, which is lasso. Lasso is a method. It's a single model can perform feature selection and prediction just using one model. There's no separate wrapper feature selection and then learning the predictor steps at all. Just the lasso itself can select feature and perform prediction just using one model. So this is called embedding approach. Question here? All right, so now, sure.
So the first one, it says ranks features independently of the predictor. So how does
there's
it rank?
no predictor at all.
So on what basis does it rank?
Yes, so that's exactly the next page about. All right, so how do you rank features? If not using a predictor, you have to use some kind of evaluation metric, right? There are some classic metrics in the literature. So for example, the very classic metric is called correlation metric. This is the Pearson correlation, and I hope you learned it in your maybe probability 1 class. Yeah, maybe 2 or statistic 1. So this really just the covariance of this feature versus the y variable. So the upper is calculation of covariance. So this is just the covariance between this xi this x variable versus the y variable over the variance. So here xi, yi means the samples. And so this is the feature x. Then if you have feature z, then use correlation just to, so in the end, correlation is just a normalized covariance. So assuming you have a data is x and z and are the features. Yeah, it's a little confusing that we use x and z here, so yeah, so in the end, so let's just assume a very simple case. I have a f function. I'm trying to predict f function from a 2 feature input space into the output space y. And we treat x feature and z feature as they're just random variables. Y output is also a random variable. Then I'm just calculating the correlation of x and y and also z and y. If correlation of x and y larger than correlation of z and y, if I can only train a model with only one features, I'm going to get rid of the z features. Because the correlation of x and y is higher than the correlation of z and y. Questions? And the equation is there. I don't want to explain it because this is, you should already learned in the basic probability class. variance over normalized. Sure.
What if there are more than 2 features then?
Then you just assuming you have x1 to xp features, x1, x2, come to xp, and then you just do correlation of x1y, x2y, x2 onto xpy. You rank them. You pick the top, assuming d features, but that's how many d. It depends on you. This is the generic situation, this is the simplest situation. Only 2 features. So you can tell sometimes I write very quickly and then maybe later you cannot tell my handwritten notes. So hopefully you can get it later. I just going to add a little bit more notes. Okay, so it's very simple. So why correlation? Because correlation is, first of all, it captures the relationship, linear relationship of a feature and the target variable. And also this correlation metric is unit independent. It's always bounded by -1 to 1. So let's look at the figure. So this shows you a situation. X feature and Y feature are completely positively correlated. So this means Rxy equals to 1. And this right figure shows you equals to 0.5. And this figure shows you there's no correlation at all. So why this is good, if you think about it, why should I pick X features if the correlation of X to Y is 1? Why should I select this feature? Just because its correlation is 1.
That way you can get rid of Y feature, just keep X.
Because it's almost equivalent to when you know X, you know Y. It's just really strong relationships, right? Of course, this is an important feature.
Then why is -1 not as significant as +1?
This is also important. So the only not important is actually this. Is the absolute value is the importance. Sorry, I understand what you will ask. What I should have is absolute values. Yes, good catch, yeah. I hope you understand how he got me. He was trying to ask, so if you do this ranking just according to Pearson correlation, and then that means those -1 Pearson correlation will be bad features. That's a good catch. I did something wrong here. We should rank them according to the absolute values of the correlation. And this will guarantee those are close to 0 are the bad features. So this is also good feature. Because when you know X, you actually can almost guarantee the -X is the Y. But this is just totally not, right? Because you almost know nothing if you know X, you almost know nothing about Y at all. So those correlations to be really, really low, actually we don't, if you, according to just this univariate relationships, we don't want those features. So there's one thing I want to emphasize is there's some distance called cosine used it's a very important distance measure in information retrieval. The cosine is actually just a special case of Pearson correlation. So if you look at this equation, a cosine is just X and Y doing in a product, right? if you look at this, if your x vector is actually 0, it means the mean vector of x, if it's 0, y is also 0, and the Pearson correlation is exactly cosine similarity. And cosine, because there's no, so that's just very popular, and I hope there actually should be more discussion about why cosine is a good measure, and so I'm going to leave that out for offline discussions. All right, so that's Pearson correlation. There's another metric called t-test. The t-test is based on some other assumptions. Pearson correlation is about linear correlation of x and y, right? So t-test is actually based on Gaussian distribution.
Could you go back to the slide before?
Yeah.
Where you have like x and y.
Yeah.
So in this case, y is the output or just another feature? Is y the output or the different
Y
feature?
is the target variable. Oh, you mean this cosine
No,
here?
when you're calculating the correlation.
Pearson correlation?
Yeah.
Yeah, so that's exactly what I tried to show here. So when you have x and z, two features, and trying to project to y, and what you're calculating is x and y, z and y, and then you rank them according to the absolute values of Pearson correlation. And it's a bounded score, which is good. You know when it's good because when absolute value is 1, you know, yes, that's a very good feature. Not like some other metrics, it's positive infinity to minus infinity. It's very hard to judge. Is it good or it's not good? Because you don't know the upper bound, you don't know the lower bound. All right, so then another metric called t-test. So I hope you still remember what is a Gaussian distribution. So this is actually for classification. So Pearson correlation, the majority for regression, and this is for classification. So in the classification, there's actually two hypotheses. You plot that specific feature you care. So in this case, I should just xi feature versus the class like y, and in this case, y have only two classes, -1 and y. It's for binary classification. So if this feature distributed, you just draw a distribution like a histogram of the x feature. The two distributions, what I mean distribution is those x from the -1 class or those x from the +1 class, if you just plot them by histogram, they totally overlap with each other, which means there's no way I separate the two features, and they tell me nothing about the differences of the two classes. So this is the left part. On the right part, it's different. You see, you can plot those x features on the class 1, those features on the class 2. Actually, this is a -1, this is the +1. You can actually tell, the two features are distributed quite differently. This actually tells you there are quite significant differences of this feature to tell you about the two classes. So this is the one we prefer, and this is the one we not prefer. We use this intuition to select features. And how do you select? And actually you have to something called student distribution, which I don't want to cover. Hopefully you already learned it in the probability class. So the null hypothesis is your feature, your x feature from the class 1 and x feature from the class 2, their mean is the same or their mean is not the same. And use hypothesis testing to get a p-value to show you, to tells you, and is it even significant against the null hypothesis? if you haven't learned about hypothesis testing, you really need to learn by yourself. Yeah. So because there's a lot of things behind this, and there's no way I talk about it in 5 minutes. So in the end, it's just this: you through the t-test, it can tells you how significant this feature really is. Follows this type of distribution. The two means are very nicely separated. It gives very good signals just from the differences of the mean to tell you the one from one class, the other from the other class. So that's the basic intuition, and there's assumption of each is the Gaussian distribution, and their variance are actually assumed to be this. I think the variance is the same in this case. Yes. And there's a lot of variation of this test. There are many variations, which there's no way we covered in the course. But so in the end, is the distance among the means significant or not? The non-hypothesis is there's no differences at all. So in the end, this just gives you a two simple flavor about univariate base, but you can tell the univariate base really just the x feature versus the y feature. If you have x1 to xp, you need to perform each xi feature versus the y. So maybe let me repeat because this is a little bit too maybe too abstract. So similar to what we just did for the Pearson correlation, where you have x1, x2, to xp features, you perform this test. Let's just write t x1 versus the y, x1 versus x2 versus the y. On 2, xp versus the y. And you rank according to the values it gave you. And yeah. So so that's the univariate based approach, but actually there's a lot more, something called information gain, mutual information. There are many more. So there's a table in a few slides. I summarize the list of univariate features. There are also materials in our reading section about if you want to learn it and where should you read. And then let's move on to multivariate filtering approach. So multivariate filtering approach is a lot harder, actually a lot harder compared to univariate based approach. Because univariate based approach, what you do is really just single feature versus the y. And then the performance, if you think, is all just an OP cost, cost that pairwise calculation is an OP cost operation. But when you look for to select subsets instead of each at a time and then rank them through ranking, and the problem really comes to how do you select the subsets? And how do you even evaluate the subsets? So the evaluation of the subsets, there are a lot of metrics too, called group correlation or something called Markov blanket, which has a lot of things behind. I'm not going to cover. And what I want to emphasize today is about how do you select subsets. So why do I even want to select a subset instead of using the univariate approach, right? Because hopefully just it can help me filter out the bad ones and then just leave all the good ones from univariate xi versus y. So this figure gives you a very classic reason why we want to select subsets. Who can give me a guess? So let's just use the correlation, or actually, this is a classification. So you can actually tell if you use the t-test intuitions I just showed you. So forget about, so this is the x1 feature, this is the x2 feature, and star versus the circle means two classes, and also the color, yellow or red, means two classes. Assuming I'm doing univariate feature selection, so I'm trying to select x1 feature according to its relationship to the two classes. So you don't even need to look at everything above. You only need to look these surrounding regions, because you only consider x1, right? If you only consider x1, the star and the circle, they are completely overlap with each other. If you only consider x1. I hope you understand that. So who has question about this? If you only look at feature 1, which equivalent to you project the features, project everything down to the x1 coordinate, that just single coordinate, which on the x1, from left to right, these are the yellow, maybe class 1, and the red class 2. They completely overlap with each other. Same thing happened for on x2, right? You just project everything onto x2 because I only look at x2 and y, right? So that's exactly what we try to say, univariate. Well, how do you do univariate? T x1 versus the y. T x2 versus the y. And it can tell you, it tells me nothing if I only look at x1 to separate the two classes, to separate the green versus the red. And the same thing happened in x2. If I only look at x2 coordinate from the lower to the upper, and all these two classes, green and red, completely overlap. But actually you can tell these two classes are very nicely separated through some kind of combination of x1 and x2. If I can write, you either just simple line x1 plus x2, but that's not the best. But actually the good feature is, assuming this is C1, this is C2, x1 minus C1 times x2 minus C2. It's almost the best feature, right? x1 minus c1, so this gives me like a minus on this side, and this gives me a minus on the downside. If the multiplication is positive, that's a red class. If the multiplication is negative, it's the green class. That's the best classifier ever. So this actually tells you the interaction among x1 and x2 is important. It's almost the best feature in this case. But if you use univariate feature selection, you're going to miss the best classifier using that interaction term. Question here? So now if I tell you there are x1, x2, up to maybe x10 features, and actually is the something like x3 and x4 interaction term is the most important features. And how do you even select this without in the beginning, like, I do not know, is like 3 features, or 2 features, or 4 features, or even maybe 10 features all interact together, right? So what's the search operational O? I want to select, I want to know the subset, which subset give me, hopefully there's some kind of evaluation metrics to give me which feature is good versus y of which feature is bad. So maybe let me write that the other way. It's x selected, I1, it's hard to know even how many. So in the end, so how do I represent a subset? How do I represent a subset? I'm trying to select a subset from x1 to xp. What is a simple strategy to show who is selected, who is not selected? It's a binary flag, right? I want to have a binary flag on each. It's a theta vector. If it's selected, it's 1. If it's not selected, it's 0. And this is a p-dimensional vector. So in the end, if you think about it, subset selection is a task looking for a theta vector. Theta binary vector. And that indicating how do you select. Okay, so what's the size of the theta vector? Possible size. Two to the p, right? Because for each position there are two choices, there are total p positions. 2 to the p. Which means, how do I select it? I need to enumerate every one of the 2 to the p choices if I want to do a complete good search about good possible subsets. And the cost is extremely high because it's exponential, right? 2 to the p. And we don't even consider how do you do assessment of each of that theta, selected theta parameter, and then you got those features, and then you need to perform the evaluation step, right? So that also has a lot of cost. So this is O2 to the p times the cost of evaluating a specific theta. The search space is extremely large. And yeah, of course, you know 2 to the p, right? All right, so, but still, like, this type of feature are very, very important. For example, in the situation like text sentiment classification, you want to read a product as good or bad or neutral. And so, of course, you don't want to just use the single feature like good, and those combination feature like a not good, you have to treat a not good together as a feature, right? It's very necessary to evaluate the combination of words in this case, not just single words, but combination of words. Question about this? I feel a little bit dry. Maybe you're a little confused now by now. So words, n-gram, if you think about n-gram, it's a type of feature combination. A-gram, like, so very good, very good, or not very boring, like fantastically interesting, and all those type of combinations. For sentiment classification, the combination matters. Yeah, so what I was trying to show is if you do univariate, it's highly likely than not, it's highly correlated with the negative sentiments. But if that's like not boring, think about not boring, and if you're willing just to not boring actually is positive sentiment, right? It's an interaction, it's an important subset to search for. and we have to model or search. But the search space is extremely large, it's OP2 to the P. So especially you might think like 2 to the P is not large, right? Let's think about our word example. What's the P here? It's, if you're a native speaker or whoever work on NLP, whoever worked what should it be the P roughly? Actually 30,000. 30,000. It's the minimal number you normally use. P in this case is actually roughly 30,000. 2 to the 30,000. All right, so this is just how do you perform a multivariate subset feature selection. You need 2 different modules. The first module is a measure for evaluating that subset. The second module is a strategy to search that subset. So based on what we represented, you need to be able to evaluate theta, and you also need to be able to search theta. And of course, it's NP hard. So you can actually plot that search, all the search through this DAG structure, directed acyclic graph. And this includes all the 2 to the P, and it's a path from 0, 0, 0 to 1, 1, 1. This 0, 0, 0 means no feature is selected. 1, 1, 1 means all the features are selected. If you only allow 1 mutation on a binary vector, this gives you P. The first layer is P. There are P different theta. And second layer is, you can keep, so it's actually pretty easy to P, and then all the possible paths. In the end, the summation is 2 to the P. In the end, you're trying to search on this DAG structure. And there's actually no way you enumerate one just a P, just a little bit large. There are many different greedy or heuristic-driven search. I think I had it later, so I had it in the next wrapper approach, because wrapper approach is mostly subset-based approach. So I'm going to cover that. So this, before I move to wrapper, the filtering approach is, the summary is, it's really very fast because it's more a simple statistic-based, correlation-based analysis, and it provides generic selection of features. It's more a predictor agnostic. It doesn't couple with any predictor at all. But that's also one of the criticism people question about this type of approach, because it's not optimized to a specific predictor. It's very generic. And it's actually still used a lot as pre-processing because fast and intuitive. And this is a list, and feel free to check it out. Actually, in scikit-learn, there's a lot of filtering-based approach already implemented. And I'm going to put the API, so hopefully you have time to read those, what are implemented there. So then let's move to wrapper approach. We want to use a predictor to select and also to assess a feature subset, hopefully to train a better predictor by using less features. So in the wrapper approach, that predictor you're going to use are considered as a black box model. You just feed in the theta, you actually feed in the subset selected version of the X. So in the end, you have a theta, use theta, you got P prime based, it's n times P prime feature. Use theta to select n times P prime matrix, and you just feed in together with the y, the predictor, the output, so your x and y, and you train a predictor based on the results, the learned model, and you use it to score that subset according to the predictive power of the learner trained on the subsets. And your result will vary. This is not a predictor agnostic approach because it's really about that predictor cares about this feature or not caring about that feature or the feature subsets. So I already emphasized many times how to measure the performance of a learner and how to search in the space of all the features. So like I told you, because of the 2 to the p search space, right? All this category of method use some kind of greedy-based search. Greedy-based search, the most classic and simple approach is forward selection. The other is backward elimination. So what is forward and backward? Let's go to see this. Forward means, okay, I start from nothing, and from a 0, 0 vector of theta, I'm trying only the 1, 0, only the one of the feature is selected. I'm comparing all those theta cases with only there's only one in one of the elements, and you rank them, and you pick the best. So that's your current selected feature. And based on that selected feature, assuming we selected second features, and then we just go on by keeping that second features by trying all the rest. So second feature is selected, and then we try condition on second feature is selected. Should I select the first? Should I select the third? Should I select the fourth? So the cost of this search is, in the beginning you have p positions to pick, right? To select, that's OP. And when you already select one, condition on that one, you have how many to select? P minus 1. When you have 2 already, you condition on that 2, you keep adding ones on that theta vector until at some stages you stop. You decided to stop. So that's why, so this should be plus, right? It's a multiplication, yes. So p times p minus 1, p times 2 until p minus t is forward. This is called forward selection. And the backward is really just the backward from this vector. You remove one feature at a time. You rank them. You pick one of the feature to be removed. Sorry. If you do reversely, and that's the one, and then you keep removing according to the third feature is removed. You have only 3 choices to remove. This is called backward deletion. Forward, backward, they're both polynomial cost. They're polynomial algorithms because you control it, right? You control when you stop. Question here? They're polynomial search algorithms. Yeah. All right. So the predicting power, it's okay. Now it's something very important. So you're training a classifier, right? So this is actually the next page. So I'm selecting a theta, one of the theta, assuming it's theta, how do I label that? Maybe theta I. And I get xpi, let's just use that xpi, n times pi. And I try to learn a function and y. I try to learn a function f, right? assuming that's called Fi, because it's one of the model, right? The only one of the model. How do you evaluate? You need a validation data to evaluate what's the feature performance for now. So this is one of the strategy I ask you to implement in the homework is called train validation test pipeline. You train the model on the train float or train part. You evaluate different models on the model part. And after you already selected, you decide how many features, who is the best theta star. So this, you use this to select theta 1, theta 2, until theta I, or maybe theta t. It gives you a best theta star. And then you retrain the model using the theta star to get the F, and use that F to evaluate on the test data. You can't, I'm so sorry, you can't touch the test data when you're trying to do the model selection. Test samples are not to be touched in any way, in any like fitting step or hyperparameter tuning step. No, whenever you try to select something to learn a function, you can't use the test samples at all. And this actually tries to separate model selection versus model assessment. I'm going to explain that actually just in a second, but keep that in mind. Train validation test. Now we are moving from the train test we used to trying to tell you. Actually, the train test we did before is the train validation step. Okay. Question here? Oh, sorry, I totally imposed my writing on it. Yeah, I'm going to clean this up. Let me remove my writing. Yeah. So for each feature subset, you train the predictor on the training data. You select the feature subset which perform best on the validation data, and you repeat an average. You want to reduce the variance. This is more like a bootstrapping approach. You can in the homework second programming. So this uses a train test or train validation strategy to do the model selection, right? But you can actually combine them together, perform cross-validation, because that's a more stable strategy to do model selection. And in the end, you retrain the model on the whole M1, M2 data, and you apply the learned model on M3 as your testing generalization error. Question. Actually, in a lot of even state-of-the-art papers, they did something wrong. They're performing cross-validation on whole data, then only report cross-validation errors, which is actually not correct. And you have to separate the model selection and the model assessment. Testing data could not be touched at all. Okay, so yeah, this is more like what I just did. You have theta 1, 2, 3, theta m, and on M1, M2, using M2 to select the best and pick the best to give you a theta star. Yeah, I should write validate. It's the same thing. You test or apply. In choose, it's trying to do validation. And however, it gives you the then compare that validation error, mean validation error, give you the theta star. Question about this? Yeah, this is almost the same thing. So if you do regression, you have different, you train that specific theta, you got that feed beta. So because when you train, you got a feeded beta star for that specific theta, right? Questions about this? This is the training stage, right? Feeding stage. I know that the notation is a little bit confusing, but so beta is the feeded beta star, either from normal equation or from gradient descent, fitted the best on your current training data, conditioned on the theta j selected features. Then you apply that beta j on the validation data, you got prediction error, prediction loss, and you do argmin of all, you do argmin here, you got the best theta, I should have theta j, give you theta star, then you use theta star to retrain on both data M1 and data M2. And that gives you this. And this just trying to repeat all this, but you're going to understand what I'm saying here when you code that polynomial regression task. Yeah. And when you're going to report test data is the examples you never touched. And using the beta star and also theta star, you'll learn. All right, so forward selection, backward elimination, beam search, always keep the k-best path. Not doing greedy at each stage, but I always keep the key best path that I can derive so far. This is another type of greedy, but a little bit more relaxed greedy. And there's a lot of search algorithm. I hope you already learned from the algorithm combinatorial search in the end. Question about this? Maybe steal this figure. But I'm pretty sure you're going to understand it when you implement, oh no, in this polynomial regression you don't need to select features. Yeah, forget about that. Yeah. The polynomial regression is to select the D. So you don't do feature selection, yeah. So, yeah. But the procedure actually is the same. In those cases, you really there's no theta anymore. You need to select the power, right? That's the power D. Okay, so we reduced the exponential cost to the polynomial cost by the greedy type of approach, or there are many different kinds. Now we move to the embedding-based approach. So embedding-based approach you already learned, which is lasso. Actually, the most classic is lasso and the elastic net, or those group one norm structured sparsity-based approach. There is a huge literature behind this type of embedding approach. It's very popular. It's a very active research field in the past 20 years. Yeah, structured norm. So we only learned about L1 norm, or this elastic L1 plus L2. There's also a lot called structured L1. So if you're interested, I'm going to post a paper, summary paper. Feel free to read it. And also help to optimize it. It has a lot of optimization background behind. It takes some time to learn how to optimize this type of approach. So it's specific to that learning machine. It's perform variable selection and prediction using a single model. But you have to perform hyperparameter tuning of that lambda. And this is the homework related to regression, but in the lasso case, you need to do the same thing. So we covered about regularization path, which really is, I think that's the regularization path of L1 across all the different lambda. How did each of the feature, how did each weight vector corresponding to each feature varies from 0 to non-zero? That give you a good trajectory of the importance of the dynamics, how the features interact, or the collaboration among features to predict the output variables. Alright, to summarize, you have all feature, you either use filter-based approach, and it doesn't even correlate it coupled with the filter, or you have the wrapper approach, uses the predictor as one of the evaluator to iteratively select features, with the most used are the greedy forward selection or backward elimination. And also the last approach is an embedded based lasso type of models. And actually all those three are very popular in the state-of-the-art machine learning pipelines and also toolboxes. So in practice, no method is universally better. And also feature selection is not always necessary. So that's the conclusion I want to share you. And a very related also feature manipulation is called dimension reduction. And the differences is, so in the feature selection you have 1 to P, you select into K1 to KP, right? It's really a search task, selection task. But the feature dimension reduction is mostly using some kind of transformation. It transformed the original features into new features. You're not staying in the original feature space anymore. So for example, if this type of features, and this is the feature 1, this is the feature 2, I'm actually like rotate my coordinate using this as the new feature 1, new feature 2. That's the dimension reduction, and actually in this case, so apparent, we are going to only use this feature. And we're going to talk about later why is the case. So x1, x2, and now we actually just only use g1. Yeah. So this is the dimension reduction, talk about later. So the last I want to talk a few minutes before I put out the quiz is about what I try to emphasize again and again about model selection and model assessment, the differences among the two. Model selection means estimating performance of different models to pick the best model. So my goal is to pick the best model. Model assessment is having a model, you already have the model, chosen a model, you want to estimate its generalization error, the prediction error, which means you have to evaluate on a completely unseen data samples. So this is the reason why testing data, if this is for the model assessment purpose, should not be touched at all in any of the model feeding, hyperparameter tuning, feature selection, whatever you're trying to perform. No, you can't touch it, you can't use any knowledge there. Label knowledge, yeah. So there's some other setting in the future, and we'll talk about that. For now, yes, you can't touch it. Okay, question here. This is fundamental. It's a fundamental concept. All right. So there are many strategies to do this, right? What we already showed is you split the data into train, validation, test. You use the train and the validation to do model selection, and then you retrain the model using both train and validation, and you use that model you just learned as the final model on the test to report the prediction error. This is for the model, the data very rich scenario. So a lot of deep learning situation, what you normally have is a train validation test setting. But there are a lot of cases you don't have so many like rich label data, and in those situations, the most popular approach is you on this training, those training and validation, you put them together, you perform cross-validation to do model selection. You can also do random sampling, random sample or train, and then use the rest as validation. You do multiple times, hopefully can get a mean performance, right? Because it's the randomness hopefully reduce the randomness of a specific split. And also there's some other approach called AIC, BIC, MDL, SRM. I'm not going to talk about it, but they're a good strategy to help you to do model selection. So what you're going to implement in homework is training validation test. And the code is a little bit misleading, is we ask you to do first split, train, validate, and test. And then we really use the same code to do training and validation split on that. First, you just extract the train data. I hope that's not confusing, because in the end, it's a subset separation. It's the same function. Okay, you're going to understand what I mean when you look at the template. All right, so there's something I want to talk about very quickly today, something called underfitting and overfitting. Underfitting means model is too simple, and overfitting means model is too complex. And the whole idea I want to summarize, or this, it's a gentle introduction about something called bias and variance trade-off. So don't worry about those, we're going to read